My name is Bill Owen, and I'm going to introduce the OpenStack Cinder driver for IBM's General Parallel File System, or GPFS. The GPFS Cinder driver is new in the Havana release of OpenStack. This driver allows you to leverage GPFS's scalable, high-performance data and file management solution in your OpenStack-based cloud environment. IBM's GPFS is a proven solution that is used extensively worldwide across multiple industries. When you deploy your OpenStack cloud environment with GPFS storage, all of your nodes are able to access image, block, object, and file data locally in the shared file system. This means that copying of data between services, like from Glance to Cinder, is minimized or eliminated altogether. And with GPFS, you get a rich set of data management and information lifecycle management tools, including efficient file clones using copy-on-write optimization, as well as tiered storage and policy-based migration of data, allowing you to optimize data placement by locality or performance tier. In the OpenStack Havana release, the GPFS Cinder driver provides all of the required driver functions, allowing you to create and manage Cinder volumes and snapshots. Volume placement can be optimized for locality using the GPFS FPO or File Placement Optimizer option, or for performance using tiered storage data pools. Data resilience is provided with replication level and direct I/O settings on a per volume basis. The GPFS Cinder driver supports host-based volume migration so that volumes can be migrated between Cinder storage servers, as well as policy-based migration between GPFS storage pools. Integration with the OpenStack Glance image service allows for very efficient creation of volumes from Glance images using copy-on-write optimization. And again, because we are using GPFS, enterprise features like encryption, backup, and policy-based information lifecycle management are available to you. Okay, before we start, let's take a quick look at the demo configuration. I'm using a 4-node GPFS cluster. One node is designated as the controller node, and there are 3 compute nodes. All 4 nodes are members of a GPFS cluster, so that the file system and data is shared across all of the nodes. Granted, this is a very limited configuration for the demo, but we have customers using GPFS with hundreds or even thousands of cluster nodes, so there's no concern about growing your configuration. Now we can begin. First, I've predefined several volume types in the demo environment. For this demo, we'll be using the GPFS volume type. Also, there are a handful of images loaded into Glance. I've predefined my GPFS file system and mounted it across all of the OpenStack nodes. When I defined the file system, I specified that there should be 3 storage pools. First, Platinum for expensive fast storage like SSD, Gold and Bronze for more economical storage levels. The first thing I want to do is create a bootable volume using one of the Glance images. I'll choose the Fedora image and make the boot volume 10 gig in size. I'll assign it to the Platinum storage pool for best performance. The volume is available immediately. The reason for this is that we have configured the Glance image repository to also use the same GPFS file system as the Cinder repository. So when we created this volume from the image, no data was copied. The new volume is a copy-on-write clone of the image file. Now let's create a data volume. In this case, I'm going to use the Gold storage pool. And I'm also going to specify that the volume be pre-formatted as an ext4 file system and give it a label. This allows us to mount and begin using the volume immediately on a VM. We'll make the data volume 20 gig in size. And we'll create a temp volume as well. The temp volume uses the Bronze storage pool. I'm also pre-formatting temp as ext4. Because this is temp space, I will specify that no GPFS replication is needed. Only a single replica of the data is kept. The other volumes we've defined use the default setting of 2 replicas that I specified when I created the GPFS file system. We now have 3 volumes that you can see when I issue the sender list command. Let's put these volumes to work. First, we'll boot a new VM using our boot volume. I specify a key name that I created earlier so I can easily SSH into the VM. But before we do that, I want to attach our data and temp volumes to the VM also. We can see that all 3 volumes are in use by our VM. Also, with the nova list command, we can see the IP address that we'll use to access the VM instance. Let's access the VM now. I'm going to switch to the root user to make it a little simpler to issue some of these commands. First, we can verify that the label given to the file system on the volumes we've attached matches what we specified. Next, let's create a mount location and mount the volumes. You can see both file systems when I run the mount command. The file systems are empty, so let's change that. We'll create a 2 GB file of zeros. You can see that the used space in the data file system is now roughly 2 GB. Back on one of the OpenStack nodes, let's create a snapshot. But first, pause the VM so we have a consistent state for the snapshot. Now we can create the snapshot of a volume. Let's choose our boot volume for this example. We can see that the snapshot is immediately available. Again, the actual copying of data is kept to an absolute minimum with GPFS's implementation of copy on write. Now we can do things like create a new volume from our snapshot. The new volume is immediately available, again because we are not copying any data. Next, we can create a new volume from an existing volume, our data volume in this example. Again, the new volume is available immediately. Let's take a quick look at how GPFS thin provisioning conserves space. Between the sender volumes we've created and the single snapshot we've created, we have a total of 90 GB allocated. If we look at the space that's actually consumed, it's a fraction of that. So how well does this work in real life? Here's a quote from one of our internal IBM deployers. He's a system admin for a cloud system that IBM development and test teams utilize. In conclusion, IBM GPFS provides a scalable, high-performance data plane for OpenStack cloud environments. GPFS has a proven track record of providing high reliability, availability, and data integrity, and many enterprise-class data management capabilities. The combination of GPFS and OpenStack can provide many unique capabilities in your cloud deployment.